Hello everyone. Today I'm going to be talking about the tangent plane and linear approximation of a multivariable function. It is section 14.4 in our textbook. So before we start, let me try to recall the tangent line and linear approximation for single variable that you have learned already in Cal 1. So let me give you a recall of those single variable functions. So in Cal 1, you have this y equal to fx, right? So x is a variable, just one variable, and y is the output. And say you have a curve, a function. Say this is a problem that you see in Cal 1. Find, given a point on the function. This is my function f of x, and this is a point, say x naught, y naught. Find a tangent line through a point on the function. So how do you find the equation of a tangent line? You need two things, a point and the slope. A point is given right here already. And how do you find the slope? The slope is the derivative, right? Slope by definition, derivative of the function at the point. So the slope m is f prime at the point x naught. So you have the slope, you have a point, you find the equation of the line. Y minus y naught gonna be equal to f prime of x naught times x minus x naught, right? Y minus y 0 equal to m times x minus x 0. This is called the slope point or point slope equation of the line. Okay, that was in Cal 1. And we're gonna carry very similar way of finding the tangent, but now it's not a line anymore. Now it's 3D, so it's gonna be a curve. So what you're gonna have in our courses is, say you have a surface. How do I draw it? Okay, this is surface. So I have z equal to f of x comma y. You imagine this is a surface, all right? And you have a point on the surface, and this point gonna be x naught, y naught, z naught, right? You plug in x naught where x, y are variables and z is the output. So the point is x naught, y naught, and z naught. Now you don't just have a tangent line anymore, you have a tangent plane. So imagine that you're looking for a plane that is tangent to the surface at the point x naught, y naught, z naught right there. Okay? And this is how you have the equation for the tangent planes, which is similar to this. Z minus z naught is going to be equal to, now you have both x and y, right? So let me just write down and explain it to you. Fx, remember what it means by fx? Partial derivative respect to x at the points x naught, y naught times x minus x naught plus fy at the point x naught, y naught times y minus y naught. And this will be your equation for the tangent plane. Okay, so we learned about the partial derivative before. Fx is what? The rate of change on the x direction, right? So you have a curve, you have a surface. Okay, this is the x, y, z, x, y, z right here, surface right here. So with respect to the x direction this way, you have a point, right? So if you go along the x-axis on the surface, see, you can calculate the rate of changing of the z value. This is going to be fx, just like right here, you have what? F prime, it's just one variable, so what? The slope is what? The rate of change. Slope is what? y2 minus y1 over x2 minus x1, rise over run, right? The rate of change in the output based on the x. Now we have two variables for the input. We have x and y, so we do partial derivative. The f over the x right here tell you the rate of change with respect to the x direction. And similarly, fy right here is the f over dy or dz over dy right there will tell you the rate of changes in the y direction. This is how we understand the formula. But I think there's a better way, in my opinion, to explain the equation for you. Recall how we find the equation of the plane as we learned before. We need two things. We need the normal vector, and we need a point. Right? After you have the normal vector, say, and you have a point, then you can find the equation of the line. What was that? A times x minus x naught plus b times y minus y naught plus c times z, this is my c, okay, minus z naught equal to 0, and then you have the equation of the line, right? So you really need is the normal vector and a point, and you find the equation of the line. Okay? And I think it's a little bit too soon to talk about it for now in here, but let me just mention it anyway. So fx right here and fy right here is rate of change. Think of it in terms of vector this way. You have a point on the surface. It's going to be x, comma, y, comma, z, right? Z, which is fxy. Let me just write it. F was, how about z? All right? This is a point on the surface. Now, remember when you take the derivative? Now I'm going to take the derivative of the vector in terms with respect to x. So dr over dx. You're going to have what? 1, comma, 0, comma, if I call it f, so z is f, right? So this is fx. Okay? It's a little bit too soon because you guys will learn that later, but I think it's another way to approach the formulas that's going to help you to understand it better instead of just giving you the formulas. Try to talk about the similarity only. Okay, this is the tangent vectors respect to the x direction because I am differentiating both sides respect to the x by a partial derivative. And similarly, I got dr, call this vector u then, and then dr over dy. It's called vector v then. It's going to be what? X derivative with respect to y is 0, y over y is 1, and then this is what? Fy. Those are the two tangent vectors. Okay, so x direction, so this is vector u. Y direction, this is vector v. And you know what? When you have two vectors, two tangent vectors, you cross product the two vectors right here. You take u cross v, or v cross u, doesn't matter. Okay? And we learned how to do cross product already. You see something like fx, fy at -1, or negative x, y, and 1. Either way, you cross those two. And you have the normal vector. This is a normal vector, right? Cross the two tangent vector. See, u cross v. It's going to be the normal vector. Right? You have the normal vector. You have a point. You plug in the formula that you learned before. We have the tangent line as well. This, I think, in my opinion, is better explanation of how you can figure out the tangent line. Tangent plane. Okay, but this is a formula that the book gives you. It's the same thing. Okay, it just didn't talk about vector yet, and I think it's more effective if I mention vector in here. You can have the tangent line as well. It's the same thing. It's just you guys can learn this later. Okay. So this is what you have, or something called the equation for the tangent plane. So what we learned in this first part of 14.4 is what? Given a function in 3D, all right? Z equal to fxy, so it's like a surface. And if you are given a point called x naught, y naught, z naught, just like a point on a function in one variable function. Here, you have a point. And they ask you to find the tangent plane. So what do you need to do to find a tangent plane? You calculate partial derivative with respect to x, you calculate partial derivative with respect to y, and you plug in this formula right here. Just like when you want to find a tangent line, you do what? Find the derivative. Now just one variable, so we don't call it partial derivative. Just f prime, okay, and plug in the point. Plug in the point. You have the slope, and then y minus y0 equal to slope times x minus x0. Similarly, you have the tangent plane right here. Okay, that was the first part. Let me see if I missed anything on a tangent plane. I should tell you more. Nope. So let's move on to linear approximation. Okay. What is it? What is it about linear approximation? I should not erase it. Leave it from here. Oh, I can rewrite it. Say this. You want to approximate the function using a linear function. Means what? Using a line. In this case, right here. Say you have a curve, right? You don't know what it is. you have a function. You want to approximate that function. So if that interval is small enough, then that curve right here is approximately like the line. Not the same, of course, that's what we call approximation, but close enough, the error is small. Okay? Recall what we wrote right here, y minus y naught is equal to f prime of x naught times x minus x naught, right? This is the equation of the line. It's not the same as a curve. You see the curve in this particular example right here. The curve is slightly below the tangent line. But the gap or the difference is pretty small if you talk about small intervals. So this is really the equation of the line, and this is really the linear approximation of the curve. So I don't know what the curve is, but I know that y right here for the curve. If you talk about the curve, then what? F of x minus y naught is approximately equal to f prime of x naught times x minus x naught. Again, this is y, okay? This is the line. And it's exactly the same. But if you got, this is f of x right here. Oh, I wrote right here, f of x. So it's not the same as the line, but the error is small. So if I replace y, which is the value on the line, by the value of the function, it's not the same anymore. That's why I use this two wiggling sign right here. It means approximately. Okay? So this is the approximation of the function. Not the same. It's called linear approximation because we are using the formula for the line. So really, fx is approximately equal to f prime of x naught times x minus x naught and then plus y naught. I'm just adding y0 on the other side. That's all. And they call this the approximation of the function. Now I'm talking about the function right here. Function is approximated using the tangent line equation, a linear equation of the tangent line. And that was the whole meaning of it. Okay, so how do you approximate the function? If you know the derivative of slope at a specific point, you don't know the whole thing about the function, because if you know the whole thing about the function, then you don't need to approximate anymore. You know little, you know a point, you know the slope at that point. Okay, then you can claim that what? A piece of the function close to that point, x naught, y naught, will look approximately like the line right here. And again, one more time, it's not the line, it's the curve. A little bit off the line, but the error is small if you're talking about a small piece of the function. So close to that point, x naught, y naught, the curve can be approximated using this formula. That's what it's saying. And similarly, right here, you see, you carry over from cut 1, right? You have this right here. So this is really the tangent plane, right? So if you talk about small interval, so f changes a little, now we have two variables, and y changes a little, and you have this f x comma y minus z naught is approximately equal to fx. Can I skip that part because it means fx of x naught, y naught, right? And then what? X minus x naught. Let me just write down the whole thing for you. X naught, y naught times x minus x naught plus fy x naught, y naught times y minus y naught. And now I'm talking about what? The equation of the surface. Of course, if you have the function already, then you don't need to approximate. But say you don't have a function yet, but you know little. You know partial derivative. You know partial derivative. You can approximate the function close to the point x naught, y naught, z naught using this linear approximation right here. So you add z naught on both sides, and xy approximately equal to this plus z naught. Okay, and you can think of z naught as what? F of x naught, y naught, which is z naught. Same thing. Okay, and this is called the approximation. And not really, you know, not really a big deal in my opinion. You know the equation for the tangent plane, and you understand what it means by approximation close using a line right here. Carry everything from cut 1 to cut 3. Okay. Now let me talk about one more thing before I can give you an example. And it's something the book called the total differential, I think. Total differential. Okay. You know it this way. dz is equal to fx times dx plus fy times dy. I'm getting lazy, so fx is fx, okay, and then x minus x naught, y minus. So what is saying in here? First of all, let me double check on the book, see if I write the name right. Total differential. Yeah. So what it's saying is this: the change of z is depending on the change of x and the change of y. And how are they related? Little change of z is equal to partial derivative of the function times the change of x plus partial derivative with respect to y times the change of y. Now you calculate little change of z. Okay. So in other words, if you know the errors in the x direction, you know a little error on the y direction, you put in this formula, you'll be able to calculate the error on the z direction. Okay, in terms of approximation, right? Which is fx is calculated, fy calculated, and dx and dy is at the error. Okay, so let me extend the concept a little bit more. Instead of having z equal to fxy, which is a function of two variables, right? Two variables. Say you got w is equal to f of x, y, and z, and this is a function of three variables, x, y, z. Now I cannot draw anymore because we have four-dimensional space, but we can carry over all the things that we learned right here. The differential dw, the little chance of w, make a guess, is what? fx dx plus fy dy and what? Plus fz dz. And what does it mean? Partial derivative with respect to x times change of x, partial derivative of y times change of y, plus partial derivative of z times change of z. And this is the change of w. Okay? And same explanation, say in physics, right? You have a function, something of three variables. And you know the error for x, you know the error for y, you know the error for z. You plug in here, you know the errors for w. Okay? Actually, this is, the book gives you a pretty good, a simple example. Say you talk about volume of a box. I need some room to write, so let me write here. Say box. Looks like the box here, right? This is x direction, this is the y direction, and this is a z direction. So the volume is x times y times z, right? So volume is like the function f. Okay, it's three variable. This is f of x comma y comma z is equal to x times y times z. So apply the formula that we have right here. It's pretty general. It's dv or df is what? Fx dx plus fy dy plus fz. Oh, parentheses in here. Fy dy is fz dz. Okay? And then if the questions say what? The error for x is about 0.1, the error for y is about 0.2, error for z is about 0.15, for example. Can you calculate with some unit length right here? Okay, say centimeter, millimeter, or something. Okay? And then you can calculate the error for calculating the volume. What? You calculate fx, fy, fz, and then plug in those numbers for the x, dy, dz. Okay? D here means little change. Okay? But in reality, we cannot calculate d, so we use the notation of delta. So delta x, delta y, delta z means to change. And this is pretty small. Okay? So what is fx in here? I'm giving you a very simple example. So in here, fx, this is x, y, and z. I'm sorry. Fx is y times z because I think of x as the variable and y is the constant. And similarly, fy is xz, and then fz is what? Xy. Okay. So you plug in the values you have for x, y, z, and the error count for x, y, z, you can have the error for the volume. That was the idea. Okay. There is one thing that I need to emphasize when you guys do your work. Make sure that we understand it right, so pay attention to this, okay? So they ask you to calculate two things in your assignment, dz and this dz. Both got dz, okay? And how do you understand the notation? This delta z means what? Z2 minus Z1. What? The initial z and the final z, subtract the initial z, and this dz is the total differential that I gave you the formula. This is what? dz over dx, which is fx, okay, time dx, plus dz over dy times dy. Okay, so let me give you an example, a simple one. You see the difference between those two, and they both calculate the change of z. This is called what? Increment of z, or this is what? The differential. Just little change. That's what I said. Let me try to give you just a simple, easy example, just to demonstrate the formula. How about this? Z is equal to x times y squared. Example. Okay? And I have x change, look for the numbers as they have in the book. X change from the point, how about 1, 0? It means what? X equal to 1 and y equal to 0, right? Change to 1.1 to 0.2. It means what? X change from 1 to 1.1 and y change from 0 to 0.2. What is the change of z? All right? And they ask you to calculate the two values right here, delta z and dz. That's, I believe, what you guys are going to see in the homework. So for delta z right here, you just simply calculate the final z, you calculate the initial z, and you do a subtraction. So z2, this is your final, this is x1, y1, this is x2, y2. z2 is what? x2 times y2 squared, so plug in a number. 1.1 and times 0.2 squared. This is your z2. Right? And similarly, you calculate z1 is what? 1 times 0 squared. Well, this is easy for me. This is equal to 0. And this is 0.04 times this 1.1 going to be 4.04, I think. 0.04. 404. I suck at math. Let me just use a calculator. 1.1 times 0.04. Enter. 0.044. That's good. Okay. So delta z is z2 minus z1. And you take this 0.044 minus 0, then you have 0.044. That would be the change of z, the total change, right, of z. All right. And then the second half of the question you will see in the homework is calculate dz right here. They call total differential. This is called the increment of z, total differential. Okay, so you plug in the formula. So if z is that, so dz over dx, or if you call this as a function f, then what fx, that's what it is y squared. Okay? And then similarly, dz over dy or fy, differentiate with respect to y, I have 2xy. Okay? Now plug in the formula where how to calculate dx and dy right here? Well, dx is delta x approximately equal to 1.1 minus 1, which is 0.1, and dy is approximately delta y, which is 0.2 minus 0, which is 0.2. Okay, and plug in the formula. dz is dx over dz over dx right here, and plug in the number for the initial point. Okay, right here. Is that right? Is 0 squared, which is 0. I didn't choose good numbers because I got a y equal to 0. That's why is everything equal to 0. 2 times 1 times 0, which is equal to 0 again. Okay? So dz is 0 times